So number 9, balance. Oh, you know what? You're talking about balancing.
Yeah.
Let's start back from the beginning for balancing. I don't want to balance just yet. This was warm up. This was just some talking points before we move on to balancing, because there's a reason why we balance. Why? Are you in the English class? No. Never mind. Sorry. Why are we balancing? Like they just made an announcement. Right? Okay. Why are we balancing chemical reactions? It's on the board. Okay, you just repeated what was on the board. Tell me why.
Because reaction, no elements are lost or gained.
Right, no elements are lost or gained, no atoms are lost or gained. What goes in the reaction comes out of the reaction. Does it look the same? No. So things are rearranged, right? So things are being rearranged is basically the premise of all chemical reactions. It just looks different. We call it different things. Sometimes it looks like a gas. Sometimes it looks like a liquid. It just depends what's going on. Yeah.
So, how would you, is balancing like, for if,
Use your words.
if like you lose matter because it turns into a gas and.
You would still say the matter is conserved because you didn't actually destroy it, but ensure that it is masked though.
Do you balance to like count for that?
Yes.
Okay.
Because if you could, I mean, you can encapsulate it. You put it in a closed system, a closed container, and you could encapsulate it and capture it and mass it. You're assuming it's still there. Yes. Okay, so if we see reactions, there's some things that we know that we see, and we're like, oh, that's totally a chemical reaction. What were some of those evidences of chemical changes from Unit 1? Think back. Fizz, so like gas evolution, right? Big words, gas evolution. What else? Bubbles, gas evolution, okay? Heat, okay, so heat. What comes with heat? Sometimes. Flames and fire, okay, what else? Okay, so rust is a specific example. Electricity is a specific example. Go bigger still. You're still talking about broad terms. Why?
Because this is just I know I can see this from here.
I'll leave this in front of you. Okay, so things like, you could also say cold. What else? What's some of those things that you put two liquids together and it makes a solid? Precipitate formation, right? Sometimes you actually see these unexpected color changes, right? So you actually have done a lot of chemical reactions already, but now we're going to start to talk about them more in depth and test for some of the products that are being made and balance our chemical equations and so forth. And we also know things come in lots of varieties. You know, we've got compounds, we've got actual elements. Which of the elements are generally our gases?
Noble gases.
Okay, noble gases. Yeah, what else? What else? Non-metals in general. So when you're looking at the periodic table, generally everything on the upper right-hand corner is going to be our gas. They're generally all gases, and then 75% of the materials over here are most of the periodic table is solid. Mercury is like one of the only liquids. Bromine's a liquid, but everything else is solid. So we're going to start really identifying those factors that we need to be kind of paying attention to. All right, so on the things you balance, before we get to balancing, we know what balancing is. We've done it, right? But there's this multiple choice that people don't do so hot on, and it's because it's like very scientific lingo that's being used in the multiple choice questions. This is the scientific lingo of what balancing means. Atoms of reactants simply get rearranged into products. Does that make sense? Yeah. Carbon and hydrogens and oxygens get moved around and make CO2 and water. But that's the lingo, so I just want to point that out. If you need to write that down, write it down. But whenever we're talking about reactions and why do we balance and what's actually happening, stuff gets shifted around and we call it different things. That's it.
And what does that mean?
This is the premise of all chemical reactions. Rxn is reactions for whenever I write it out. And this is the premise of what's happening and why, I don't know, not why. This is just why we balance, I guess. Because we balance to prove that the reactants are still present, those atoms are still present, so we just call them products at this point, though. We all know reactants are on the left, yielding products on the right. Yes, this is not new. Okay. Bear with me here. Yeah. I just was trying to point out some of those things that sometimes you're like, oh yeah, I get that, but then you forget like the lingo used whenever we're talking. Okay, so on your first reaction, we have it. Did we balance this one together? Yesterday? All right, that was a 1 to 1 to 1 to 1, right? I'm not going to balance that one again. And that's because all the subscripts accounted for it themselves. This one, thumbs up if you got this reaction. Yeah, okay, cool. whatever you're balancing this one, I'm just going to walk you through my process once again, and then you can kind of modify it for your own. But at this point, do we add any subscripts? No. When you're balancing, you're only adding what? Coefficients. Okay, so the first thing you see is magnesium. How many are here? 1. There's no imaginary 1 there. How many magnesiums are here? 1. Imaginary 1. That magnesium is good. How many chlorines do you see? 2, because there's 2 times 1. It's multiplied. So 2 chlorines there, 2 chlorines there. We're good there. How many oxygens over here? 6. Not added, right? It's multiplied. 2 times 3 is 6. And then over here, I only see 2. So what coefficient do I add here?
3.
A 3, because the 3 times the 2 makes a 6. Okay, so on yours, just add your coefficients. That's all you're doing. So then you double check again. You're like, yep, that's a 1, that's a 1, that's a 3. That's it on balancing. So you guys tell me how to balance this one. Thumbs up if you got that right, first of all. Because you put your diatomics. That's the one that people usually mess up on. All right, how do you balance this one? What are you starting with? Okay, sulfur, is it good or not good? It's good. Next. Oxygen, so you see.
A 1 or a 2.
So how do you make 2 equal 3? You can't, right? You go to the least common multiple, right? So basically everything here is multiplication. So if you can't make 2 equal 3, you got to multiply them both by something to get them to the next common multiple. All right, so 6 is the next common multiple. So what do I put in front here? 3, and then in front of here? 2. But then now what have I done to sulfur? So you add a 2 back over here. So it's not trial and error. You have a process. It's just you got to watch. If you mess up something else, you got to go back and fix the first thing you've already thought you had balanced. So 2, 3, 2 is ratio. There we go. Next one. Who got the correct chemical equations? Okay. So tell me your thought process here. Starting with silver. I see 1 silver over here. I see 1 here. Good. Next. Nitrogen. How many over here? 1 and 1. Oxygen 3. Oxygen 3. Sodium. Sodium 1. Bromine. 1 and 1. So that one's actually balanced. And you can kind of visually see that probably up front because you don't see any subscripts except for the 3's. And so that's really all you're looking for. Yeah.
Is it okay if we put PBT instead of S?
Yes, totally fine. Because solids are, precipitates are solids, but not all solids are precipitates.
This one for like copper, I put.
Yeah. I generally put solid because it's recognized as a state of matter, but it's a specific state of, or specific phenomena, which is the precipitate. So it's either way, it's good. Okay, we're going quickly. Next one. Tell me where to balance. Or you guys have it on your paper, you can balance on your paper. Oxygen needs what? But this oxygen needs a 2?
No, that.
So water, so you're saying water needs a 2, right?
Yeah.
So if I put a 2 in front of water,
We need to put a 2 in front of hydrogen.
the hydrogen to make 4. All right, thumbs up if you're getting this. Okay, because I think you've done this in like 7th grade. Yeah? Okay.
Put in some grade, like avian and that's what you have.
Okay. So we'll look good because then now you're actually doing the whole shebang by yourself. You're writing the reactants, you're writing the products, you're balancing it, and then we're gonna do more with it. You're gonna be pros, people. Okay, next.
You need another oxygen on the left side.
So I'm gonna put what?
A
2 in front of mercury.
Add a 2 in front of
The mercury. Okay. Use your words. Yeah, mercury. So 2 and 2 there. Yeah.
I would put a 2 on HGO.
This mercury, oops, mercury has a 2 plus charge, right? What's oxygen's charge? 2 minus. So they cancel out, right? That's what a lot of people messed up on that one in my last class too. Okay, next one.
We can have delta over the arrow for the next.
Yes, I'm sorry. I didn't actually. It's hard to put that on
Yeah.
compete on this thing. Heated to produce. This one doesn't have any conditions present. Okay, this one was a little bit of a harder reaction, but you got it. I'm hoping if you wrote down what your individual reactions and products were. This one I want to. Well, no, I'm not going to show you. You guys tell me what needs to be balanced. Potassium is good on both sides, right? But the iodine needs to be balanced, so put a 2 in front of potassium iodide. And then now you've messed up potassiums, right? Now you got 2 potassiums, so what here? 2, and then what does that mean you have here? two. I'm gonna call that two nitrates. I want you to see that nitrate stays together. It's a happy family, right? From here to here, nitrate's a happy family. Don't be a homewrecker. Don't break it up. Nitrogen and oxygen, 3, they go together. So how many nitrates over here?
2.
2 nitrates here. How many nitrates now over here?
2.
2, because I applied, because that coefficient applies to the rest. But there originally was 1, but if you put a coefficient, it applies to everything past it. So there are 2 nitrates there, there are 2 nitrates here, there's 1 lead here, there's 1 lead here. So we're good, yeah? Okay. Oops, there we go. So here, what do we need? So I'm going to put a 2 in front of aluminum. Here, I see 2 and you said 2.
You need 1 more oxygen.
But how do I get 1 more?
You have to multiply the
Okay.
oxygen on the left by 3.
Okay. And then on the side?
By 2.
By 2, but now what have I
But then
done?
you have to multiply the aluminum on the left by aluminum has to get a 4.
So sometimes there are coefficients we have to change, and it's okay. But try to keep going through your process. Once you change one, change another one.
Wait, hold on.
Yes.
So you don't change that other. Now you don't change the product aluminum.
Right. Because I did, because you guys told me to put, you saw 2 oxygens and 3 oxygens, so to multiply
Six,
out,
yeah.
so that 2 there means now you do have 6 oxygens, but you also have 4 aluminums, and so I had to go
Okay.
back and fix the first coefficient that I've had originally. Good. All right, this one, think of it as happy families, okay? So we have, what polyatomic ions do you notice? Okay, so ammonium and nitrate, and I'm just going to put parentheses around them for your sake. There's ammonium. Okay, how many magnesiums do I have? 1. How many chlorines? 2 and, so what do I need? Coefficient of 2 over here. Okay, that means I have 2 chlorines, but also 2 ammonium. Sorry, 2 ammoniums. Do I have 2 ammoniums over here? No, so what do I need here? A 2. Okay, so now I've got 2 ammoniums. Good. Also, that means I have 2 nitrates. What do I have over here? 2 nitrates, and I'm good. So sometimes you can do it by individual element like magnesium and chlorine, but if you have a polyatomic and you want to consider it as a whole, it is totally fine to do that. Generally, our polyatomics do not get broken up, so they're not going to change. Last one I think we did, except for balancing. This guy. Okay, so what do I need?
2
Hold on, go in order, because you don't just jump straight to 2 and don't think. I heard 5 and I heard 2, right? So tell me what your process is. 5 in front of the oxygen, and then, oh, maybe that's what you guys are talking about, that PO5, okay. Phosphorus, pentoxide, so that's 10 oxygens,
But then you have 2 phosphorus, so you have to put
a 2 here, good. I know my numbers look weird, but yours look better than mine. Okay, good with balancing. We're going to keep practicing. So, next thing we're talking about are types of reactions. What are the 5 types of reactions? Combustion, my favorite. What else? Decomposition, things breaking down. Single replacement, double replacement, and combination. Another word for combination is synthesis, yes. So if you can think of synthesis by taking 2 things down to 1, decomposition from taking 1 thing into many. Single replacement is like, girl really likes this guy, but he's got a girlfriend, so she like blackmails the girl, and then like they fight, and then he takes her place, right? The guy never really moved. He's just like, all right, next. And then another example, double replacement, if couples, doesn't matter gender, couples say, oh, I really like your significant other, but I really like your significant other, so let's just switch for the day. Okay? It happens all the time, right? But that's basically all reactions are.
We need to kick the sophomores out more often.
We have our mature conversations with our juniors. Okay, so these are the types, but I'm not going to do all these today because I don't think your brains will handle it well. I'm going to stick with these 2 today. Okay? So we just do those today. We'll call it a day. I want you to do these first because these are decomposition have 4 different types of decomposition. So I think it's good for you to see it earlier than later, because then remember, every day you see it, the better you know it. Okay? So you don't have to write down much here. Just write down synthesis and decomp, or S&D copy. And that's what we're talking about today. Okay, and I'm gonna start you off. Let's start you off with a video. Let's look at types of reactions. Oh, tell me when you're ready. Start your video. Give me a little break here.
What kind of cake is it?
I don't know, but it's yummy cake. What other kind of cake is there? Yes. Okay, let's look at amazing chemical reactions. You ready to be wowed? Okay. You will be wowed. What is this?
The bright side of carbide.
What is this? This is Pandora.
Speedy oil change and auto service.
Okay. Okay, so back to chemistry. Pandora. Alright. This is just to wow you. Ready? This is not exactly. This is just chlorine and cola explosive. No, it makes like some sort of gas that's not good for you. Cesium and water. So this is like mini. This is slow-mo explosions. Craters on because it's nothing in this. It's the surface area. So anyway, there's like mini explosions going on here. There's phenolphthalein, there's lots of pink. Huh? No. This is copper coming out of solution to make copper on the iron nail here. Single replacement reaction actually. Time lapse, of course. Soap and milk. You guys know this? Yeah. Coloring. It's so cool. I talked to a professor at UC Charlotte yesterday. He never heard of this. I was like, how have you not heard of this? This one's cool. You light mercury thiocyanate on fire, and it grows into this oxide thing. It's like this snake. Kind of. On it, and the muscles contract. Muscles contract. It's dead. It's not alive. The muscles are simply contracting because of the salt channels. Yeah.
I would be terrified. Like,
who eats cuttlefish? Some cultures do. Never mind. They're going to eat it. Plus they're going to touch it. There's like another minute maybe. Not even. So this is calcium. We're making calcium oxide. Calcium's in a lot of fireworks. Well, mercury thiocyanate. Who's the last one? Yes, last one. We'll watch another one later. We watched the crazy Russian chemist hacker. Yes, we watched that earlier. It was awesome. Okay, so types of reactions. Here's your notes for now, and we'll watch another video in a second. There are two really big slides of notes. This is one of them. Then we'll do some practice, and there's another one that we'll do some practice, and I'll let you guys practice and do notes. Oh, I gotta slow it down.
Start recording still.
I think so.
Just real quick.
Yeah.
Yeah, we'll go to voice.
I mean, like,
Like ours.
Is there a
No,
pretty
I
loud?
don't usually hear like Steven's voice.
Yeah.
I don't know.
You're good there?
Yeah.
Are you on the second example?
No, first.
So you guys probably saw in your notes or your reading guide. Synthesis was also called what? Combination. It kind of makes sense, right? Combination simply just means combining two things together. And so we have two different types. Whenever we combine things, we combine them into one product, which is the premise of synthesis. You're synthesizing one thing, making one thing from multiple things. So the first one is called binary. Why does this one make sense in terms of the word binary? Just two elements, that's it. Just like any binary ionic or binary molecular compound always has element 1, element 2. Give me your favorite metal.
Gold.
Gold. Okay. I'm going to say gold with a 3+ charge, okay, because it's a transition metal, so I got to tell you what it is. And your favorite non-metal?
Oxygen.
Oxygen. Okay. Oxygen like that?
O2.
With O2, okay. And then, my bad, that's not solid, that's probably a gas. Just saying, oxygen is a gas here. So if I synthesize these, I absolutely, positively have to look at the charges and crisscross the charges. Every single time I make an ionic solid, I have to crisscross charges. So if I tell you gold is 3, you know oxygen's charged, right? So tell me what the product would be. Au 2O3, because in your head you did Au 3+, oxygen 2- and crisscrossed. Even though it's oxygen gas here, it still forms an oxide. It still forms an ionic charge with a O2- charge. So just don't forget to do that. Now balance.
You put 2 in front of the gold.
2 in front of the gold. Okay, I'm going to write it there for now. So you need a what? A 2 in front of the gold what? Oxide?
Yeah.
Oh, gold 3 oxide. Why do we need a 2 here?
Because you have to make the oxygen 6.
Yes. So what do you need here? 3. So then what does that do to gold?
It makes it 4, so you get 4.
There you go. Yeah.
Why is it the 3+ charge?
I just told you that because it's a transition metal, and I have to tell you the charge of a transition metal.
But that doesn't go in the equation.
It doesn't. Yeah. Good point. You do not write. If I said gold 3, you do not write it there. You think about it before you crisscross. So that's why I wrote it up here away from you, because you do not write gold 3. That is just gold solid. Okay. So that's our first one. Metal oxides and water. Metal oxide, give me a metal. Not gold again. Platinum. Let's go representative just so we can get the charges. Lithium oxide. So what's lithium oxide when you put it together? Li 2 O, because Li has a 1+ charge, oxygen is a 2- charge, crisscross. Okay, and water is just water. So when it goes together, it makes metal hydroxide. And now, how do you remember this? Basically, you have to smush it together, but you can't just smush it together and just put like MOH2O, because that just looks dumb, right? We're gonna say it, because if it doesn't look like something you've ever seen before, it's probably wrong. So you got to morph these two things into something you've seen before. So one thing you've seen before is hydroxide. So water and O, oxygen, comes there and make hydroxide. All right, so it's going to make lithium hydroxide. What is that? Li. OH. Why are there no subscripts? Li has a 1+, hydroxide is 1-. Do you see how nice it is to know your polyatomics now? You do not have to look them up. You know this stuff. That way you get through your problem. All right, this is not balanced though. What do I need? 2 in front of lithium hydroxide. Does that satisfy all of our problems? Yeah, it does actually. Lithium gets a 2. It's got a 2. O, there are 2 O's here, 2 O's here. 2 hydrogens there, 2 hydrogens there. That 1 actually balanced the whole thing. Cool. Okay, so video. Next guy. This guy. Yes. All right, you don't have to write down anything. This guy, I'm running him double, or I'll run him 1.25. That works.
Hi, it's Mr. Anderson, and this is Chemistry Essentials Video 29. It's on synthesis and decomposition reactions. If I were to ask you which of the 2 reactions you see on the left is a decomposition reaction, the tendency is to choose the rusting railroad car. And the reason why is it looks like it's breaking down. But if you think about it, what is rust? Rust is a combination of iron and oxygen, and so this is actually a synthesis reaction. And so if we ever take atoms and molecules and combine them together to make a new compound, then we've got a synthesis reaction. So what's an example of a decomposition? The breakdown of water into oxygen and hydrogen gas is going to be an example of that. And so if we take atoms or molecules and we combine them together to form a new compound, we call that a synthesis reaction. We're making something. Likewise, if we take a compound and break it down into atoms or molecules, we call that a decomposition reaction. Lots of times that'll generate a little bit of heat. And we can use both of these reactions in the chemistry lab to do simple stoichiometry and practice our lab techniques. And so synthesis reaction are when we're taking atoms and molecules and combining them together. So let me give you a couple of examples. Let's say we take magnesium, get it a little bit hot, and then allow it to combine with oxygen. It's going to make magnesium oxide. And so when it's done, you're going to have a new solid that's created. We're taking a solid and a gas, and we're making a new solid out of it. Another example of a synthesis reaction could be the carbonation of water. And so this is me adding a little bit of carbon dioxide to my soda stream at home. And what's going to happen inside there is that the carbon dioxide is going to combine with the water, and it's going to make carbonic acid. So that carbonic acid is going to lower the pH to around 4, and it's going to change the taste of that carbonated beverage. What's decomposition then? It's when
What do you notice just happened? He's talking really fast. Now what happened to the reaction?
He flip-flopped.
Just flipped it. So decompositions are just flipped of synthesis, right? So if you know your syntheses, then you actually know most of your decomps.
we're taking a compound and breaking it down. So here's an example. If we take sodium azide and break it down into sodium metal and nitrogen gas, that'd be a decomposition reaction. So if we have one reactant and 2 products, it's a good idea that this is probably a decomposition reaction. Where's an example of this actual reaction? Well, this was used in early airbags. And so what you can do is you can put some sodium azide inside the bag right here. It's totally stable, but if you add a little bit of heat to it, so there's an igniter inside there, it's going to quickly break into sodium and nitrogen gas. And that nitrogen gas is going to fill up the bag really quickly. Now you can imagine a bunch of nitrogen in there is not a good thing. That's highly reactive as well. And so they also put chemicals in here that react with the sodium. Another example could be right here. I'm taking hydrogen peroxide, and then I'm simply adding a catalyst to it. I'm adding an enzyme that's found in yeast. And so the yeast isn't part of the chemical reaction.
So you said the yeast or the catalase. You guys remember catalase from biology?
Yeah.
The biology that we had the liver. I don't know if you guys did that. Liver.
Where you
And,
cooked it in potato or something.
yeah, you had celery, potato, liver. If you tested the activity of catalase, which is the enzyme, you'll notice it does not say catalase in here. Where would it say it?
Above there.
Above the arrow, okay?
And it just serves as a catalyst. And so what I can do is I can add hydrogen peroxide to it, seal it up, and I can give it a little bit of a shake. And what it's going to do is it's going to break down into water, and then it's going to break down into oxygen. And that oxygen is going to fill up the bag. Now, if you feel the bottom of the bag, it's going to get warmer and warmer. And the reason why is that we're releasing energy as we break those bonds and form new bonds to the point where it can eventually explode. And so sometimes you have to let a little bit of that gas go.
It's pure oxygen. It'll catch on fire. It would make a big explosion. Just saying.
That scared me. So did you learn the difference between a synthesis and a decomposition
Cracked me
reaction? Hopefully. And this one,
Scared me. It's just random at the end. Okay, so let's do these syntheses reactions. You guys can come up here, okay? So start a couple on your paper, and I'm going to ask you to come up here. Before you have what you want. This is not on your notes anywhere. You're writing down the reactants and your yielding products. That's it. No math. Except for in balance, but you know. I don't really call that math. I feel like that's almost math. So how many volunteers for the first one? I can volunteer. I need to. maybe I'll do 2 for you with you. Remember your diatomics. If you're writing anything in the big 7 in hydrogen by itself, it's not really by itself. It has a mini-me. JK, it's got a 2 next to it, right? So what's the first one? H2. Okay, so this is a synthesis of 2 elements. Dun dun dun. 2, right. So why did you just put H and Cl, no subscripts? Because H plus, and which is the element, and then Cl minus, which is the other element, which is the ion form, crisscross to make HCl. And then you said to balance it by putting a what? 2 there. Okay, so you just take the element and the other element, and you crisscross their charges. All right, next, you guys keep going.
Those are diatomic.
Action is start your best here. Okay, good. So we have oxygen, which is diatomic. Magnesium makes, what is this called? Name? Oh, magnesium oxide. Magnesium is a 2. Oxygen is a 2. Crisscross down. What happened? They reduced down or cancel. Okay. So those 2 were what kind of synthesis? There's only 2 types. Binary. So the next one here is what? The one with water, right? That I don't think it has a name yet. So tell me what barium oxide is. Okay, I heard Ba and I heard O. Think about what the charges are. Okay, 2 plus and 2 minus, so they crisscross to make what? The 2 minus. Okay, BaO plus water, and what is it? What generally does a metal oxide and water make? A metal hydroxide. So what's the metal here? Ba. So barium hydroxide is gonna be our product. So you say it to yourself: metal oxide plus water makes metal hydroxide. Say that a couple times. Look right to your notes. You'll remember this. Plus, there's not a whole lot you can do. You're synthesizing. But barium hydroxide is what's the full formula? I hear OH, but you just told me the charge of barium. Yes? Right. What's hydroxide's charge? 1 minus. So Ba 2 plus and hydroxide makes BaOH 2. Half the parentheses, the 2 only applies to hydrogen. You want it to apply to the whole hydroxide. So you got to be able to know or find your charges. You don't have to really know your charges, but find them. Okay, so those are syntheses. You have a couple of examples to look up through later. Decomposition. This one's the bigger slide. We'll do those. This is the bigger slide. This one I'm going to leave you alone for a couple minutes because there are 4 types, right? So binary, metal carbonates, metal hydroxides, metal chlorides, and that's how they decompose. So I'll be quiet and let you guys write down what of that.
So where did they go to?
I'm literally in the same place you guys are.
Because when I was in the auditorium for Chilton, there was like this band setting on. I don't know what that means. They had like,
Doesn't matter. scroll down a little bit. So I'll go back down a little bit. I'm going to go back up in about a minute here or else. So we're going to talk about these types, practice them, do a demo, and then you guys will be free to practice. Okay, I'll come back down here. I want to talk about the first one first. Two of these you should kind of recognize. Which ones look familiar to you but backwards? And metal hydroxides. So you actually already know two of these. So there's basically two synthesis types of reactions and then like two decomposition reactions, but two of them are also the opposite of synthesis. So put a note here, just say opposite of synthesis and opposite of synthesis. And if you know the synthesis ones, you should be able to recognize that these are just opposite. So let's go ahead and look here. Give me an example of an ionic compound, metal, non-metal. Give me your favorite metal. Iron. Okay, let's go iron 3 oxide. Iron 3 oxide, what's that formula? Fe2O3, because that 3 came from iron, that 2 came from oxygen. Okay, if rust just split up automatically somehow, that would be awesome. If it decomposed, what would it make, metal and non-metal wise? Iron and, how do you write oxygen?
O2.
O2. If it just decomposed, that would be great. We would have no rust in the world. Maybe it does, but really, really slowly. I have no idea. So what do I do to balance?
2 in front of the other 2.
Uh-huh. Okay, so I see I need 3 oxygens here.
So you need to put a 3 there and then
What
a
over
2
here?
in front of the rust.
Uh-huh. So really I need 4 there. I was hesitant. There we go, my 4. Okay, so you can do this, it's just opposite. Let's go ahead and jump down to the metal hydroxide one. Give me a metal hydroxide. Not the one we just used though. Copper 2 hydroxide? Oh yeah, sorry, I need a hydroxide. So copper 2 hydroxide, what's that formula?
Cu.
Uh-huh. OH2, because you said copper 2 hydroxide, so it crosses down. Okay, so what does it create? Copper what oxide? 2 oxide, because you told me this was copper 2. And so remembering that's copper 2, when you write it again, you write copper 2 plus, oxygen 2 minus, so crisscross, what do you get? CuO, because the 2's and 2's cancel. So that's copper 2 oxide and water. Okay, balance? Or is it balanced? It's balanced. 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. We're good here. Okay? So the 2 that are different, here we go. Metal carbonates make carbon dioxide. Carbonates make carbon dioxide. So that one really should resonate with you to make carbon dioxide. So if you just remember CO3 breaks down to CO2, that one is going to make your life a little easier. So let's just give me a metal carbonate. Give me any metal and I'll put it in carbonate form. Zinc carbonate. Ooh, that's a good one. What's zinc's charge? 2. How do you remember that? Memory. That's how that works, right? The Z looks like a 2. That's how I told you to remember it. So zinc carbonate, what's carbonate's charge? 2. So 2, 2 goes down to 1, 1. So CO3. So ZnCO3. And I'll put a parentheses there just to make sure you recognize that's carbonate. It's going to break down to metal oxide. Well, before I do that. Carbonates always break down to carbon dioxide. So you automatically know one of the products. So your job is to make sure you account for every atom here. Zinc hasn't been accounted for, neither has the other oxygen. So that's why we make zinc oxide here. So what's zinc oxide? ZNO. Because the 2 from zinc and the 2 from oxygen go away. So, balanced? Yes, it just happens to balance itself in this one. 1 carbon, 3 oxygens on both sides. So carbonates make carbon dioxide. Then your last one's a little harder. You're like, chlorates make, that's what you want to say, right? But chlorine would kill us all. Do you think I'm going to give you a reaction that will kill you? No, just homework. Just homework, right? Okay, so chlorine gas would kill us. So your lesser of the 2 evils is not to make chlorine gas, but to make oxygen gas. So if you're looking at chlorine or chlorate with chlorine and oxygen in it, you're trying to figure out which gas to make, choose the less deadly one. Okay? Keep yourself alive. So you're making oxygen gas. So let's do potassium. Give me potassium chlorate. Okay. Where are the subscripts? They're 1 and 1, right? So 1 plus for potassium, 1 minus for chlorate. Okay? Makes oxygen, because not chlorine. And then metal chloride. What's the metal here? Potassium. So potassium chloride is what? KCl, because it's 1 plus and 1 minus. Balance? No. Balance. It wasn't a question.
Well, you're gonna have to.
Oh, hold on. I heard a 3 in front of the oxygen because you saw a 3 here. So if you put a 2 here and then 2 there. Okay. Cool. So we see that we have 4, but 2 of them are the really new ones. Okay. So on your paper, do these 3. There's only 3. Do those 3. These are decompositions. Look back at your next section. We're almost done here. Sorry, and actually only do the first one and the third one. We just did that one, didn't we? Yeah. You're probably starting to write again. You're like, this looks familiar. I'm also taking much better notes than we have in the past because I think your learning is very useful. Good to have stuff to look back at. So hold on, let me check it out here. Sodium carbonate, go. Lies. 2 CO3. Shame on all of you, because sodium is a 1 plus charge, carbon is a 2, crisscross. Okay, decomposes with heat to. Hold on. Carbonates break down to carbon dioxide. So I'm going to go ahead and write the gas first. Carbonates, carbon dioxide. Okay? What are we missing? Na2O, thank you, Connor. So we're missing a sodium oxide. We're missing a metal oxide in the middle there. Okay, so balanced? Totally great. Okay, we already did that one. Water. Oh my. Water breaks down to what kind of decomposition would this one be? Binary one, because it's just element and element. It's not a carbonate, it's not a chlorate, it's not a hydroxide. Technically, it's a binary element or compound. So what's it break down to? O2. Balance? Balance.
You have to put 2 before the water. 2 before the hydrogen.
There you go. Oxygen's already now accounted for. Okay, so you've got your reactions. You're gonna practice those more in a minute. I'd like to do a demon. Demonstration. I was gonna say demo, and I was gonna say demonstration. I just meant demon. I'm gonna do a demo, guys. Let's go back here. You just have to stand back a little bit. It's a fire reaction. This is a decomposition reaction. Let's do this demo. Okay, so I have before you potassium chlorate. What does potassium chlorate break down to? Decomposition. Nope. That would be too easy to potassium chlorate. That is great. But potassium chlorate breaks down to chlorate make oxygen and what's the remaining step? The metal and the chloride is potassium chloride. So it's going to make oxygen, right? So it's going to decompose and make oxygen, but I've got to make that over. Okay. So we got to decompose this first. So what I'm doing is making it molten. So I just got to melt this baby up a little bit. But oxygen is going to react with this gummy bear. This is a gummy bear, not that. This is a gummy bear. Oh, okay. I thought so you were confused. This is a gummy bear. What is a gummy bear primarily made of? Sugar, like what? Glucose. If you make if you put glucose in the presence of oxygen, what happens? Good question, Miss Inlo. Yeah, I know that. So, glucose in the presence of oxygen makes it's a combustion reaction. Like in your body, how do you combust things in your body? You're combusting things right now in your body. This is taking forever to melt. Your body does it through cellular respiration. You remember glucose plus oxygen makes 36 ATP? Yeah? Fine. You're like, no. Okay. I have a lot of potassium chloride here, but way too much. So this should be good. Go big or go home, right? Okay. So basically, glucose is a hydrocarbon, meaning it's got a lot of energy in it. We put in the presence of oxygen, it combusts. What does combustion mean? Explosion. Yeah, give me the chemical composition of explosion. What's the chemical composition of explosion? Carbon dioxide in water and other stuff. Man, oh man, let's do this, man. We're waiting on you. Oh, sorry, I put a lot of my. Wait, so it's just gonna take just wait. Let me get the oxygen going first. I'm still decomposing this. Apparently it's not a very good time. How do you know? Okay, so you see it's becoming molten. You see it becoming molten? Yeah, it's slowly. Okay, and if you were really close, you could see bubbles of oxygen. I mean, you could see bubbles. I'm just going to oxygen. Okay, so it's making oxygen gas. And in 3, 2, 1, we're going to have a boom. Chemical composition. Not loud. So here we have lots of oxygen. The gummy bear! So the gummy bear just combusted, right? It'll smell like s'mores in here soon. Okay. We will. We'll do s'more geometry. Okay, we have 2 reactions there. We had a decomposition reaction, and then we let the oxygen react with the gummy bear to debate what kind of reaction. Combustion. And then I can digest it, decompose it if I want to eat that, because that's what you guys do. So, let's go back. You guys will finish practicing. The s'mores is another day. No, but we will. That was so you guys have 25 minutes left. You're going to practice about 5 problems from me right now, and then you're going to have time for Mythbusters if you need to talk to that person, because I know you need a little time. So on the first, I'm really excited to see what they're doing.
They had to have gotten in trouble for something.
Yeah, they were talking about them, and they're listening to it. Still big.
I'm telling you, there was a guy with a violin, a guy with a guitar, and a guy with a drum setting up in the auditorium doing kids music.
So it's something. So it's like performing?
Yeah. They did class for us.
Okay. Why were we not invited? Right?
Yeah.
That was
Oh, didn't we have that music came in and was like Jackie Robinson? No.
I don't remember that.
No,
Okay. Anyway, back with me. There's people's papers. Yeah. Okay. Thank you. I will wait on you. I will make you do all 10, or I'm going to ask you to do 5, but I need your compliance. So right now, under synthesis and decomposition, you'll see there are 5 under each one, right? So I want you to choose 5 total, not 5 of 1. So maybe 2 from here and 3 from here, or 3 from here and 2 from here. Split it up. Try those right now, and then you can work with the Mythbusters partner, and we will finish the rest of these tomorrow with my people who are gone. Okay? So, get her done. You eventually will have to do all 10, but right now I'm asking for you to do 5. Yeah, pick what you want. And you may not have room on this paper to write, so you might need to write someplace else. There you go. It's in the student packet. And I've been trying to print some stuff for you, but the student packet is well established.